So today we're going to talk about polarity, not just of a bond, but of a whole molecule. But first, let's talk and remind ourselves about just the bond. Just the bond, let's do CCl, right? Just the bond, CCl. Let's determine first, is it polar or nonpolar? Just the bond, is it polar or is it nonpolar? So can I remind you guys what a molecule is? A molecule could be just carbon and chlorine. It could just be that. But a molecule is two or more atoms. Two or more atoms covalently bonded. And remember from yesterday, the word covalent, we reminded ourselves covalent means, here I'll do this in purple, shared electrons between two atoms, and it is between non-metal and non-metal. And yesterday we were looking at just the bond and figuring out, is it a polar covalent or non-polar covalent? Okay, so let's look at this bond, carbon and chlorine. Let's figure out if just this bond is actually polar or non-polar. What is the electronegativity? So turn to page 174 of your textbook, and you could have just one or two out at your table. 174. In your workbook. Good. Alan, what is the electronegativity of carbon? 2.5. Good. Nadia, what's chlorine? $174. Do you see chlorine? They've assigned it a number. It's different than the numbers we've known before. Is it something like 3 or 3.1 or on the right? Second. 3.0. So remember that number is its electronegativity. Nani wasn't here yesterday. That's why I picked Nani. But it's this number that we've assigned that says, how badly do you want an electron? So chlorine wants an electron with a number of 3.0 versus carbon wants a chlorine of a number of 2.5. So which one wants the electron more? Chlorine. And in fact, how much more? You do the absolute value, the difference. A difference of 0.5. And we know from our work from yesterday or our textbook work, our lecture, that 0.5 is in fact polar. So this is a polar bond. And when we're talking about polar, we're meaning that chlorine wants the electrons a little bit more, right? So when you're looking here, chlorine wants the electrons more. How much more? 0.5 more, right? And I'm going to scroll up really quick. Do you remember where did I put it? Right here, our difference in electronegativity. So if you're above 0.4, so 0.5 is in fact polar. Non-polar is anything that's 0.4 or below. Okay. All right. So what we can do is we can assign this what's called a dipole arrow. Here, we'll do this in red. A dipole arrow looks like this. It's an arrow that we can assign, but it's got a little tail. And this is the more positive, and this is the more negative. And what I mean by that, so if we've got our carbon-chlorine bond, which one wants the electrons more? We said the chlorine. And so the dipole arrow looks like this. We put it toward the chlorine. That's the direction that the electrons tend to flock over toward. And we put the little positive tail. You guys see how that looks like a plus? Right here. This kind of looks like a little plus. That's not an accident. That's because it is a slightly positive area. And why is that? Carbon and chlorine are sharing the electrons. It's just the electrons are hanging out or going toward the direction of chlorine just a tad bit more. So now let's look at a whole molecule. Now that we've reminded ourselves what an actual polar bond means, let's look at a whole molecule. And the question is it polar or non-polar? In order to determine if this is polar or non-polar, we're going to have to do a couple of steps. First, we need to draw the Lewis structure. So then that way we can figure out its molecular geometry, or that's a fancy way to say its shape. And then from its shape, we can determine polarity. So this is a three-step process when you're looking at a molecule. All right, let's do an example molecule. So let's do carbon tetrachloride. Carbon tetrachloride. So first step is to draw the Lewis structure. So we need to look up the valence electrons. Remember that? Doing a valence electron inventory. How many valence electrons does carbon have? 4, yeah. So 4 are coming from carbon. We've got 4 chlorines. How many do chlorine have? 7. Good. For a grand total of 32 valence electrons. All right, so if you're like, wait, what? What did she just do? The 4 is the number of valence electrons from carbon. This 4 is because there are 4 chlorines, so you're going to multiply. And then this 7 is because chlorine has 7 valence electrons. Yeah, remember that? Now we know how many valence electrons we're working with. We draw the skeletal structure, and which one is the central atom? Carbon. So we have, we've got carbon in the middle with 4 chlorines. So we have dealt with 2, here I'll highlight, 2, 4, 6, 8, right? There are 8 electrons being shared. So let's go ahead and subtract them. We're left with 24 electrons we still need to deal with. Remember, we put them on the terminal atoms first. Each chlorine right now only has 2 with that shared bond. How many does it want? What does it want to achieve, chlorine? octet, right? So it needs 6 more. Mathematically, if you can figure this out, there are 4 chlorines. 6 times 4 is 24. Boom. All right, then that's why we have 24 left. So we just put our 6 around each chlorine. So there's 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Now all of our chlorines are happy. They've all achieved octet. And is our carbon happy? Yes, right? Because it's got the 2, 4, 6, 8 shared bonds, right? Shared electrons around it. So everything has achieved octet, so there's the Lewis structure. All right, so now we need to figure out the shape of this. So the first step is, what is its electron geometry, meaning how many electron clouds are surrounding the central atom? 4. Good. It just so happens all 4 of those electron clouds are actual bonds. They're not, none of them are lone pairs. So both the electron geometry and the molecular geometry are the same, right? And what do we call something with 4 things around it? Tetrahedral. Good. Tetrahedral. All right. So let's now put our dipole arrows on our Lewis structure. We know, I'm going to scroll up just a little bit, we know that chlorine is more electronegative than carbon. So the electrons are going toward the chlorine. So that's what you do. You draw the dipole arrows. Now, unfortunately, a Lewis structure, remember, is 2-dimensional. It's 2-dimensional. So let's remind ourselves of what this tetrahedral shape looks like. It has a central atom with 2 atoms in the same plane, and then one going behind and one coming forward. So one going behind and one coming forward. And I've got the model right here. And if you recall, all of the angles are 109.5. Remember, that's because all 4 of those chlorines are repulsing each other, or repelling each other, and they want to get as far away from each other as possible, and that's exactly at 109.5. So here's the 3-dimensional model right here. Here's what I want to ask you, because page 175 shows you a tug of war, and we know that this individual bond, the chlorine's winning, isn't it? The electrons are flocking toward the chlorine. Now here's the question about the whole molecule. If all of the electrons are pulling in the direction of chlorine, does this molecule move if it was a tug of war? Does this molecule move? No matter what way I put it, it's pretend like they're little people pulling, and they're all pulling equally. Does it move? Natalie's shaking her head. Gabe's shaking his head. You want to tell me what you're thinking, Natalie? Why? Yeah. So I have a question. It's easy for us to visualize 2 people playing tug of war, pulling equally. Would they move? No. That's something linear. We can visualize that. Visualizing 3 dimensions, Natalie's right. They're all the same angle. They're all pulling equally at the same exact angle. So this thing also does not move. Just as if it were just 2 people pulling back and forth equally. Now this, but remember the one bond is unequal, but they're pulling, 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 pulling. This does not move. Now, because of that, we can say that carbon tetrachloride is a nonpolar covalent, of course, because it's shared electrons. Nonpolar covalent molecule because the individual bonds and in fact the individual polar bonds are all pulling equally. All right. All pulling equally. Now I could do the same exact molecule, or well, not same exact. I could do a similar molecule, but let's do methane, which is CH4. It looks like this. Okay, so we've got carbon tetrachloride and we've got CH4. They look very similar. So is this tetrahedral? Yeah. Right, it's got a carbon, a hydrogen, a hydrogen, a hydrogen, excuse me, a hydrogen behind, and a hydrogen coming out into the universe. One thing that we have to figure out first, though, what is the individual CH bond? Is it polar or nonpolar? Is it polar or nonpolar? So, carbon, what's the electronegativity of carbon again? You could look it up. What is it? 2.5, right? And what's hydrogen? I think I have it. Is it 2.1? Am I right? Yeah? Okay. So we'll take the absolute value. So this is a 0.4. So what do we call the type of bond that has a difference of electronegativity of 0.4? Nonpolar. Yeah. So this is nonpolar because of this. Now, this molecule CH4 is a non-polar covalent molecule because the individual bonds are all nonpolar. So if you look here, I'm going to scroll just a little bit. CCl4 was nonpolar because the individual polar bonds were all pulling equally. Versus CH4 is nonpolar because there is no pull at all. The individual bonds are all nonpolar. This whole thing is nonpolar. So they're both nonpolar, but for two different reasons. Did you also notice that I didn't put any dipole arrows on CH4? It's because there is no dipole arrows. There is no flow of electrons toward one thing or another. Now, I mean, technically carbon wants it a little bit more than hydrogen, but it's so subtle that we don't even acknowledge that there is a little bit of a difference in electronegativity. Anything 0.4 or less is almost negligible. You don't have to worry about it. Okay? Do you see how these two molecules are both nonpolar, but for different reasons? Now I'd like to show you one other molecule. And this is H2Cl2. H2Cl2. So let's figure out what the number of valence electrons are. Okay, let's see. Carbon has 4. Hydrogen is in that first column. It only has 1. And we know chlorine has 7. So what's that? 14, 16, 20 valence electrons. Carbon is always the central atom, so we'll go ahead and say C, and then we'll put the H's here and our Cl's here. Are we good? Yeah? Does it matter if I put the 2 H's and 2 Cl's? Like, does it really matter the order of the Cl's or the H's? No, it doesn't. It's your preference. So I have dealt with 8 of these valence electrons by the shared bonds, so I've got 12 left. Does hydrogen need them? It only has 2 around it, but remember hydrogen is our exception. It wants to achieve duet because it wants to be like helium. So hydrogen's happy. It does not want any more electrons around it. It's achieved duet. So the chlorines, they need to achieve octet, and it just so happens, perfect, we've got 12 left over, and I got 2 chlorines. So I'll distribute the 6 right here and the 6 right here. So chlorines are now happy, hydrogens are happy, and the carbon is happy. Now we know the carbon-chlorine bond is a dipole bond. Let's go ahead and identify that with our arrow. We also know that this molecule is tetrahedral. The way it's written right now, doesn't it almost look like it's linear, like 2 chlorines are on either side of a carbon playing tug of war? But remember, this is tetrahedral. Right? This is a tetrahedral, so it would look something like maybe this is the chlorine, and then this is the hydrogen. Here, I'll draw it in a different color. That way we can see it. Yes. So the hydrogens look like that. So if you're looking at the dipole, it's being pulled this way and being pulled this way. It's almost like in a bent fashion. So here, I'll rip apart this molecule. So I'll replace those 2. Now, if you're looking at this molecule and you're visualizing this in your brain, pretend like the little green chlorines right here have a little person pulling on them because the electrons are going out that way. Would this molecule move? They aren't pulling. Here's this in the middle. Would they pull? No? So if I was trying to pull this desk and Karina was right here and I was right here and we both were pulling outward, would the desk move? Yeah. That's how I want you to think about this. You got a desk and 2 people at this exact 109.5 angle and they're pulling. Would the desk move? Yes, it would. Yeah. Because you don't have these 2 folks pulling equally. So if a pulling action can happen, this molecule is polar. So this is an example of a polar molecule. So far I've only shown you nonpolar. So, Oh. All right, so we have C, CH2Cl2 is a polar molecule because the CCl bonds are polar. And the CH bonds are nonpolar. Therefore, there is an unequal pull. Therefore, there is an unequal pull. And I'm going to leave you with this. Why do we care? Well, number one, polar dissolves polar. So if I had water, by the way, I'm going to build you water really quickly. This is water. It's got two lone pairs right here. Is this individual OH bond polar? Is this individual OH bond polar? So look at your chart. Let's do the math just quickly in our head. Let's look at water. What's O? On your chart there, Brandon, you have it out. What's O? What is it? 3.5. Hydrogen is 2.1. Is this a polar bond? 3.5 minus 2.1. What's that? 1.4? Something like that? This is polar. Why? Because now the electrons, the dipole arrow is going toward the oxygen. So here's what I want you to think about. Karina's on that side, and we're exactly 109.5, and we're going to push on this desk. Is it going to move? Yes. So sometimes there's a pulling action, sometimes there's a pushing action. This is polar. So water's polar. If I were to put some CH2Cl2 and put these two together, they would make a homogeneous mixture because this would dissolve this. All right. Polar dissolves polar. The other thing is nonpolar dissolves nonpolar. So if I had a mixture of carbon tetrachloride, the one with the 4 greens, and I mixed it with methane, these would dissolve each other. They'd be all intertwined. Again, it would make a homogeneous mixture because these are both nonpolar and they can mix. So, polar does not dissolve nonpolar. And vice versa, right? So if I were to take water with some methane, if I were to take polar water, nonpolar methane, and put them together, they would not mix. We've experienced this with oil and vinegar, right? We visually can picture oil and vinegar. They do not mix. Why is this so important that polar dissolves polar, nonpolar? It's like dissolves like. So if you can remember that, like dissolves like. This is critical for cellular function. Our cell membrane has polar sections and nonpolar sections by design. The body has designed it that way to allow certain things in and out. Also, if you think about engineering a vehicle, if you have two, liquids or fluids coming together in an engine and you want them to dissolve in each other, or if you don't want them to dissolve in each other, right? That's important. I mean, we've got radiator fluid and brake fluid and transmission fluid and oil and gasoline and I don't know what other fluid you stick in your car, but there's lots of them, and you better believe some should dissolve some and some shouldn't dissolve the other. Otherwise, the whole function of the engine won't work. So this is really quite important for understanding how things interact with each other. Tonight's homework, you guys, is understanding and naming the interactions between two different molecules. They call them van der Waals, dipole, and H bonds. So I would like you guys to do tonight's homework. Do we have time to get started? Do we have time? This is amazing. I never have time. Yes. Do your homework. Let's get our books out. And you guys, I ran out of time in first period. I don't know what I did with you guys, but this worked well. Now you guys can start to look at the names and the interactions of molecules with each other.